Hi, Chris Good here with another video. I'd like to use this time to talk a little bit about the null hypothesis, about the distribution of the t-statistic, and a little bit about the statistic called P, which stands for probability. So I want to go back to the t-test that you guys learned how to do in 3510, which is the single sample t-test. T in the single sample t-test is equal to the difference between a sample mean and some population mean with a known value. I think a good example of this might be IQ scores, where we know that the population mean IQ value is 100. Your sample mean would be the average IQ of some group that had been treated in some way. Maybe they were taking some drug, in which you might expect to improve or decrease their IQ. And of course, the S sub m being the estimated standard error of this sample mean. So the null hypothesis in this case would be that the population mean, the known population mean, is 100, and that's the hypothesis that you're going to test. So the formal wording of the null hypothesis would be that your treatment doesn't have any effect, and so you would expect your sample mean to be very close to 100. And if that were the case, then the value of t, if the null hypothesis is true and your treatment doesn't have any effect and that the population mean is 100, then usually t should be close to 0, right? Because if your treatment doesn't do anything, then the sample mean should be around 100. You subtract the known population mean of 100, and indeed it's the case that when the null hypothesis is true for the single sample t-test, t is usually 0. Remember that this is a frequency distribution where on the y-axis here we're graphing frequency. So the most frequently occurring value for t when the null is true is 0. Let's see if that's true for the independent measures t-test. Here's the equation for the independent measures t-test. Remember that we need to have a null hypothesis in order to calculate t in the first place, otherwise we don't know what to put here. So we hypothesize that whatever our two groups experienced, it isn't enough to cause any difference in what we're measuring, any difference between these two groups. So it is as though these sample means came from, reflect samples that came from the identical populations, or at least populations with identical means, so that the difference between the two population means would be 0. So we can put 0 here and continue with our calculation. Well, if you treat one group in one way and one group in another way, and the null hypothesis is true that your treatment doesn't do anything, that there shouldn't be any difference between these two groups, well, then the difference between the sample means should usually be 0 again. So the t distribution that's in the back of your book, and the one that's on this page, and the one that we've been talking about all along, is the distribution of t when the null hypothesis is true. When your treatment doesn't do anything, then t looks like this. Now, it actually looks a little bit different depending on how many degrees of freedom there are. When there are lots of degrees of freedom, then t looks normal, like you see in the black line. When there are only a few degrees of freedom, then t gets sort of smushed out and spread out. And that is why we need to look up what the critical values are for t with our degrees of freedom, because it's going to be different. The critical values for t are going to be different with different degrees of freedom. All right, back to our independent measures t-test. When we do look up critical values, we use alpha to say, well, in a two-tailed test, we have some positive value for t and a negative value for t, and when we calculate a value for t that is inside the critical region, that is more negative than the negative critical value for t, or more positive than the positive critical value for t, that's when we reject the null hypothesis. What are we actually doing there? Well, the critical regions, that is the shaded areas beyond these critical values, we know that together they make up alpha proportion of the area under the entire curve. And in the example that we're going to use here, we can use an alpha of 0.05, so that 5% of the total area under the curve is beyond these two values for t, above positive t crit, below negative t crit. We're able to find out what these values are for any given proportion under the curve, whether it's 0.01 or 0.05 or 0.1 or 0.15 or really any value, because of this equation. And we've already used calculus to determine that, you don't need to use calculus to determine that 50% of the area under the curve is above this line. And once you move this value to more and more extreme, the proportion goes smaller and smaller. We've already used the calculus to create the t-tables so that you don't have to use the calculus. You can just look up and say, well, let's say degrees of freedom are 10. What are the critical values beyond which 2.5% is in this tail and 2.5% is in this tail? Or whatever combination you want, really, if you had a good enough t-table. So again, you can only look those values up when the null is true. So what are we testing under this assumption that your treatment doesn't do anything? Well, you can't determine with any certainty that your treatment worked, even though we're going to make that assumption at the end. We're never going to really prove that that's true. We can't even assign a probability to the event that the treatment did something. In fact, we're not going to ever do that at all. And when we do end up with a probability value, that's not what that probability means. So that p-value, you may have heard folks say that, well, that's the probability that your treatment worked. But that's not true at all. In fact, that probability is only calculated under the assumption that your treatment didn't work. Let me say that again. The value for t, right? In fact, your critical values for t, all of these things are assumed and calculated under the assumption that the null hypothesis is true and that your treatment didn't do anything. But as I've said in class, we wouldn't be doing this if we didn't suspect that the treatment did do something. So what exactly are we doing? Well, when we calculate t under the assumption that the null hypothesis is true, we're basically saying, well, what if our treatment doesn't do anything? Should we expect a difference between our two sample means that's that big? If we go back to our in-class example that we've been using, which is this test to see whether ginkgo actually works or not, I'm just going to grab that slide really quick and flip back to it. We're looking at the difference between the average memory score of people who took ginkgo and the average memory score of people who took a placebo. There's clearly a difference, but is this difference big enough for us to conclude that ginkgo really works? Well, that's what we're using t to do, but we first have to make the assumption that ginkgo actually doesn't work. You assume that it doesn't work, and then we're basically measuring the difference between the two means. We're measuring the distance from here all the way down to here where this other mean is, but we're taking into account the variability of both of these distributions together. But we're doing that under the assumption that there really isn't any difference. There really isn't any difference between the two groups. We didn't treat them differently. We didn't give them different pills. If we assume that that's true, right, then any differences between these groups would be due to chance. So we're assuming that these differences in the mean are not due to a difference in treatment, they're due to chance. What hypothesis testing statistics allow us to do is say, well, how likely is it that we would randomly get two means this far apart if we just reached into populations that have the same mean, where the difference between them is 0, and we got two samples selected at random? Most of the time, if the population means really are similar enough so that there's a 0 difference between them, most of the time, these two means are going to have the same value, and therefore t is going to have a value of what? 0. Most of the time, in fact, the most frequently occurring score for this t, just as I've said, is 0 because these will be very close together. Sometimes one of them, like mean 1, is going to be bigger than mean 2, in which case t is going to be positive and it's going to move in this direction. Sometimes, just by chance, you'll have a value for mean 1 that is so much bigger than mean 2 that the value for t is way, way, way out here in the tail. Let me get a marker line so I can move that out there and show you where I'm talking about. All right? So sometimes your calculated value for t, and let's go ahead and put that right here in the slide. This is your observed value for t. Sometimes, even if the null actually is true, then this observed value for t is going to be really huge because just by chance one of your sample means happened to be much bigger than the other sample mean. Sometimes this first sample mean is going to be really, really small. Again, this is when the null hypothesis is true and you're just selecting two samples at random from a population, right? Or from two different populations but with identical population means. Sometimes mean 1 is going to be so much smaller than mean 2 that your observed value for t is way down here. Even when the null hypothesis is true and you didn't treat them differently, or Ginkgo doesn't do anything. Well, we don't know whether Ginkgo actually does anything or not. And we will never know whether the null is actually true. But we can use the laws of probability to make an informed decision about whether we suspect that Ginkgo works or not. We're never going to prove it. We're not going to prove it at all. But we are going to get some evidence that it works or that it doesn't. Let's say that we do get results just like this. And that difference, that mean difference here, relative to the variability, leads to an observed value, and we're going to say that the treatment is mean 1 and the control is mean 2, an observed value that is way, way out here. That means that people taking Ginkgo performed much, much better than people taking a placebo. Well, that's out here in the critical region. I know you already know that you're going to reject the null hypothesis and conclude, yes, this is a significant difference. But on what basis? What does that actually mean? So, what it means is that we observed a value for t, right, that is very extreme under the assumption that the null hypothesis is true. So if the null is true and Ginkgo doesn't do anything, well, we're pretty sure that it does now, right? We rejected the null, right? But we calculated all this under the assumption that it is true. In fact, this t distribution exists here under the assumption that the null is true. When the null is true, a difference this extreme between two sample means is really very unlikely. How unlikely is it? Well, we don't know. All we know is that it's less than whatever we set alpha at to arrive at these critical values for t. I said earlier that it was 0.05. So we know now that p, for this calculated value for t, is less than our alpha value, which I said again was 0.05. When we start using programs like SPSS and Excel to calculate t, it won't just tell us the observed value for t, and it won't just tell us whether the probability associated with this value is within the critical region or less than 0.05 or less than whatever alpha we choose. It'll tell us an actual value for p. And in this case, for these data, given the distribution we used in class, I calculated what p was, and it's actually very small. It's like 0.0009. That's way, way less than what we set our alpha at. So of course we're going to reject this null hypothesis under which we made all of these calculations. What does this probability really mean? Well, it's not the probability that our treatment worked, because we'll never know that. It's not the probability that the null hypothesis is true, because we're rejecting it as not true. It's not the probability that the null hypothesis is false either. What P is the probability of? Well, it's the probability of getting means that are this far apart. Let me go back to this slide. P is the probability of getting means that are this far apart. This one's up here close to 9, this one's down here close to 6. If the null is true, that is, if our treatment, if ginkgo doesn't do anything, then it's extremely unlikely that we would find these results just by chance. P is the probability that we would find these results if they were due to chance. And this is a very important distinction. We don't know that they weren't due to chance. It's possible that the null hypothesis actually is true, and you'll never know whether it is or not. All P is a probability. And even though this is very unlikely, this could actually still happen. We could take two means at random from the population, and we'd have a less than 0.09% chance of finding a value of t, like it's probably way out here, this extreme, but it's still possible. In which case, we would have made a type 1 error. We're going to reject the null hypothesis. But if it's true, and it might be, then we've made a type 1 error. Now again, P's not the probability that the null is true or false. P's the probability of getting the results that we got, but only when the null is true. When the treatment does nothing, it's possible to get these results just by chance. P is the probability of getting those results when they are due to chance. So a couple of things that you can't know from this. You can't know that your treatment worked. You can't know for sure. You can't even assign a probability to whether your treatment worked or not. You can't assign a probability to whether the null hypothesis is true or not. But you can calculate the probability of getting these results if they were due to chance. And that's not saying the same thing as calculating the probability that they were due to chance. And we'll keep coming back to this distinction throughout the course. That's it. Oh, wait. One more thing. So how do we use this information? How do we use P to help us make a decision? Well, if P is the probability of getting means that are really, really far apart when the null is true, and it's really unlikely to get these when the null is true and these differences are due to chance and not to our treatment, then we're going to decide that it wasn't due to chance. We're going to decide that the null isn't true. If the null is true, and it's really unlikely that we would get results as extreme as we did, we're going to use that information to reject this assumption and kind of throw out the whole t-test and this whole table and say, you know what? It wasn't due to chance. It was due to our treatment. We're going to take this extreme probability, not that it's due to chance or not, but this extreme probability of getting these when these differences are due to chance, and we're going to use that as evidence that our treatment really did work, that these differences are not due to chance, and that's why we reject this null hypothesis when the observed value for t is beyond the critical values. Again, that's not proof that the treatment works. And that's something that not a lot of folks understand about hypothesis testing. When you reject the null, that doesn't mean that your treatment definitely worked. You will never know whether it really worked at all. So we can't really prove anything. But it's not just ginkgo that we could test this way, but all kinds of drugs, including, even aspirin or antidepressants. Does this mean we don't have any proof that those drugs work? Well, yeah, it doesn't it means that we don't have that kind of proof where you're for sure that we've definitely proven beyond a shadow of a doubt that there's a difference between these that's caused by the treatment. But don't give up. When you find that one mean is much greater than the other, and then you change the design slightly and find it again, and then this relationship goes in the same direction, you start to build up a body of evidence. And that's really what science is all about. It's about building that body of evidence. Yes, it's based on assumptions. It's based on somewhat arbitrary values for alpha. We chose 0.05 at the beginning, and since this is much less than alpha, we're going to reject that null. But when we do the studies again and again, and we keep finding the same thing over and over again, that's when we start to build up that body of evidence that really supports a conclusion very strongly. Okay, that's the end.